Okay, thank you. So the meaning of short-phase diode is when the junction is from your electric contact. This distance in here is showing as the WN. If the WN is much smaller than the minority carrier in this side, so which means that this is a hole, right? The minority carrier diffusion length. So if this condition met, then that's we call the short-phase diode. Okay. So when you look at the short-phase diode, now is in the previous class, we discussed about the minority carrier distribution. Okay. Especially in this case, WN is much smaller than the LP. When you look at the minority carrier in the N side, which means the whole excess carrier distribution following that this kind of linear curve. Okay. And then as you remember, if the WN is much larger than the LP, then that distribution is following that more like exponential decay, right? Okay. The short-phase diode is especially for this case, and then this minority carrier distribution going to be linear. Okay. So for this particular case, we noticed that several interesting things compared from the regular PN junction diode. Okay, so these two in here, side by side, we compare the characteristic. So one is when the WN is much larger than the LP, so which means that the electrical contact in the N side is a lower doped N side is a much larger than the diffusion length. That's this case. And then right side is when the WN, this one is much smaller than the diffusion length of a hole in the N side. Okay. So as we discussed, when the WN is much larger than the LP, our excess minority carrier concentration will follow that this exponential decay. Okay. And then when we have for example, WN is much smaller than the LP for this case, our excess carrier following that this linear decay. Okay. So this result is we already discussed in the previous class. Okay. Now, in the neutral region, if we integrate all these excess the carriers, then from there we can obtain that the total stored charge. Okay, so simply Q area and integrate all the area in the neutral region for this excess hole. Then from there we can obtain the total number of charge stored in the neutral region. Okay, so same way, so this side is also is QB. We can integrate the same way using this excess hole. Then we get this result. Okay. So now in here is that based on the definition of capacitance, the definition is when you apply the outside bias, how this charge is going to be changed. So derivative of the QB divided by dVA, that gives us this stored capacitance. Okay, so that is basically the definition. So if we use this obtained QB and then apply the derivative in terms of VA, then now we get this kind of expression for the CS. Okay? So same way, this side is also, we get this one. Now, if we compare the capacitance, okay, is left side and then the right side, okay. If we have to compare the capacitance, we can have the comparison is that we have this kind of relationship, okay. So, because if in this case is that CS short means that this one represents the short phase diode, okay. CS long represent this is a regular p-n junction diode which has the very long it's contact separation. When the CS is short, which means that the WN is much smaller than the LP, okay, the capacitance for this one, CS short, is much smaller than the CS long, okay. So if you compare these two, okay, so which means that for the same given bias, if you use the very short base structure, then its capacitance is going to be much smaller than the one in the regular p-n junction diode, okay. This characteristic is especially important. Later on, we're gonna study about switching characteristic of this p-n junction diode. So when you look at how fast diode operate, if you look at that one, that characteristic directly related to this capacitance, okay. So smaller capacitance support the faster operation of the device, okay. So in that sense, if we just compare the diode which has the short phase, that short phase diode give us the faster operation compared to the long base is the diode, okay. So that is the one thing is we have to keep in mind. Another one is following the same way we can obtain the resistance for the device, and then another important thing is the current. Okay. So if we following this step and then look at the current, now is that the current in here is, if you compare with a short base and long base, okay, WN is much smaller than the LP, okay, which means that for the short base diode, you can have the much higher current flow compared to the longer, this regular p-n junction diode. So that means that for the same given bias, okay, if you look at the current in the short base diode, you will see lots of current flow compared to the long base diode. Okay, so that kind of a conclusion is we can obtain from this simple derivation. Okay. Okay. And then another topic is now we're gonna look at the switching characteristic of the p-n junction diode. In fact, this slide is we're gonna come back later on. So let's start from in here. Okay. So when we build this electronic system, is nowadays many electronic systems based on the digital circuit. Okay, so over there, the p-n junction diode itself also can be used as the simple this switching operation device. Okay, so for the switching application, ideal case is that we want to have the transition of the switching, so which means that typically 1-0 operation in the this circuit, you want to have this from 0 to 1 or 1 to 0, or we say low to high or high to low, this operation. We want to have this operation as fast as possible, okay? So for that purpose is that now we are interested in this so-called transient response of the p-junction diode, okay? So when you look at the transient response of the PN junction diode, is a PN junction diode is as a switching device. We look at is a turn-on characteristic and turn-off characteristic. We're going to look at, okay. So which means that the turn-on means that let's say initially diode was the off, so there's no current flow. Suddenly, we apply the forward bias in the PN junction diode, okay? So that you're going to start to see current flow through the device, okay? So that is the turn-on characteristic. Turn-off characteristic is initially diode operate in the forward bias, and then you suddenly is apply the reverse bias, for example. That's going to be turn-off characteristic of the PN junction diode. Okay, so both of this case is that our starting point is from this continuity equation. Okay, especially is when you look at P plus N diode. Okay, so the P plus N diode means that in the P side we use the high doped P side, N side is low doped. Okay, so for this case is that when you look at the total current, okay, when you look at the total current, for this total current is we can approximate as the whole current, okay, because simply the majority carrier of the whole, this case in the P side, that is dominant factor for the total current. Oh, just 1 second. Okay. Okay. So now is that when you look at that P plus N diode case, as I mentioned, is that the total current is approximate with the whole current. So when you look at the whole, the continuity equation for the whole, that equation is approximate with this equation. Okay. And then if you look at just 1D case, this equation is if further simplified with this equation. Okay. So if you look at the equation in here is any change of this whole concentration, okay, in the N side in terms of time, that related with our injected whole current. And then for this case is that our is recombination or generation parameters in here. Okay. So if we using this equation, now is if we integrate this equation in the N side, okay. So if we integrate this N side, then the equation in here is that the whole concentration change that turn into the total charge for the whole in the N side. Okay. And then in this side is that the whole concentration, this change, also change is total, this the charge. Okay. And then the whole this current is density. If we integrate this area, then that gives us that the total current for the whole. Okay. So now our question to look at this switching characteristic of the diode, looking at this equation in here. Okay? This is the simplified equation describing that how the injected current related with accumulated hole in the N side. Okay? And then especially, as I mentioned, is that if you look at the P plus N diode case, the hole current represents the total current for that case. So we can approximate this equation with that your total current related with is the charge change in terms of this equation. Okay. So this equation is basically described that when we have the certain input of the current in the PN junction diode, okay, that current is now start to change the accumulated charge in this N side, okay, and then that relationship can be solved by this equation, okay. So that is the starting point to look at this PN junction diode switching characteristic. So as a first example is to look at that continuity equation for this switching characteristic. We're going to first look at the diode turn-on characteristic. Okay. So simple descriptive figure in here shown this turn-on characteristic of the PN junction diode. So initially, you have a P plus N diode, okay, and then that was open, so which means that there is no bias applied in the PN junction diode initially. And then at the t equals 0, okay, at that moment is that now is you have a switch and then connect to this PN diode, okay, and then start to flow that certain current through this PN diode. Okay. So for this condition, now is we are interested is how this input current related with the stored charge in the N side. Okay. The minor carrier stored charge in the N side. From this relationship, now is we can actually look at the time variant of this current, and then also time variant of this storage charge. Okay, so that is the kind of thing is we want to do in here. Okay, so is go back to our equation. So what we are interested is, we have equation describing this switching characteristic, which is determined by this one, T plus QPT tau P. Okay, so that is the equation is we want to solve. Okay, for this particular case. Now, to solve that one is that first we need to have a boundary condition, okay, in terms of is parameters. Okay, so in here is that the condition is this is the time. First, this is let's say current. Okay, at the t equals 0. Your current is that IF, okay? So this is the condition. So if you look at the previous equation, as a previous our equation, we need to solve this one. Okay? So when the t is at 0, we connect the diode and then apply the switch on. Okay. Then our current, this one is as we discussed, the current is that this will be IF. Okay. Now, to solve this equation, the solution in here, we try to find that from this equation is that we are interested how this QP going to be changed in terms of time. Okay. So to solve this one is that what we need to do is, as you can see, if you look at this equation again, you have certain constant in this side, and then if you do the derivative of the QP in terms of time, okay, that comes out as the same QP, okay, itself with this time constant in here. Okay. So to solve this one is that the easiest way going to be, we can assume the solution of the QP. Okay. So in here is that we can assume our QP, which satisfies the time derivative of QP itself turn out the QP represented by this exponential equation. Okay. In here is of course, we don't know that the two, this coefficient, unknown coefficient. Okay. And then we have this exponential term, okay, with the tau p. Okay. Now, to solve this equation, simply you can add this QPT, okay, and then time derivative of the QPT, you can plug into this in here, and then from there you can solve this equation. Okay. So to do that in here is, as you can see, we have two unknown variable in here. Okay. So to get this unknown variable in here, we need to have two boundary conditions. Okay. So one boundary condition is that when the t equals 0, okay, so that's the beginning of this switch is on, the diode itself before t equals 0 is diode itself was open circuit, okay, at the thermal equilibrium. So which means that in the N side, if you look at the total, this the charge at the t equals 0, okay, that's going to be 0, right? Because simply before t equals 0, the diode was not biased. Okay, so this one solved first is a boundary condition. Okay. And then second boundary condition is now if t goes to the infinite, okay, when the t goes to infinite, what happens is that your current going to be saturated with this input current. Okay. So, and then your charge, of course, this one also is need to be saturated. Okay. So there is no time dependence. So if we apply this condition in here, now what we get is time variation, this one going to be 0. Okay. And then this current is saturated with IF. Okay. Now, then, as you can see, is a QP. When t goes to the infinite, this one going to be IF multiplied with a tau p. So you get this condition in here. And then this condition is give us another is a boundary condition when t goes to infinite. Okay. So you have two boundary conditions. One is when the t goes equals 0. Another one is t goes to infinite. Okay. For these two boundary conditions is that the QP first one, this one going to be 0. Okay. And when this one is QP, this one going to be tau P IF. Okay. So using these two boundary conditions, and then if you plug in to this general solution for the QPT, then from there you can get the coefficient. Okay. So when the t equals 0, as you can see, this is 0. So a plus b equals 0. Right? That's the one thing. And then when the t goes to infinite, then this is going to be 0. At that time is that a going to be this one. Okay. So from there we can obtain the a and b. Okay. And then final solution, if we summarize that one, this now we get this equation. Okay. Let's check that this solution is correct. So let's apply the t equals 0. When the t equals 0, this term is 1. So as we discussed, and then QP going to be 0. Okay? So that is correct. And then t goes to infinite. Now this term is 0. So tau P IF, that's going to be this QP. So that's the correct. So this solution going to be correct solution. Now, if you look at this equation carefully, at the t equals 0, when we apply the IF, by applying this switch on in here, now in this n side, hole concentration increased with this equation. Okay. So if we plot that one, is that we're going to obtain something like this. In the outside, if we apply the switch on for the PN junction diode, and then look at the change of the discharge, stored charge in the N side, we can see that the stored charge exponentially increased like this, and then eventually is saturated with the tau P IF. Okay, and then following the desiccation. Okay, so that kind of conclusion we can get by solving this continuity equation. Okay. Now, in terms of this hole concentration, if you look at the hole concentration, as we increased the time, so this one shows that in the N side, we look at the hole concentration. So initially, at the thermal equilibrium, there is no bias. If you look at the minority carrier concentration, which is the hole in here, that's going to be this dotted line. Okay. Now, at the t equals 0, we suddenly switch it on, and then we apply the current as the IF. Okay. Then now is that at that moment is that the number of this excess carrier is start to increase. Okay. Now, in here is that you have to understand one thing is that the current in the structure. Okay. So if you remember is that when you look at the PN junction diode, especially P plus N diode, okay. For this one is that if you look at this hole current in the structure, the hole current, this one, in this neutral region, we calculate from the diffusion current in the neutral region. Okay, so the diffusion current, this one related with is, as you remember, is that the dP dx carrier concentration difference in this structure. Okay, so this one is directly related with your Hall current. Okay, so if you understand this one, is now is for our switching characteristic at the t equals 0, we're gonna in the outside we suddenly put the diode with this IF, forward bias current. Okay, so which means that during this switching time, our current should be constant with IF. Okay, that constant, especially in this minute carrier distribution, represented by this slope. Okay. In fact, this slope is all same during this transition of this Hall concentration to represent that your current is all same as the IF, because the slope, this one, dP dx, especially the edge of this depletion region, going to be same during this transition. Okay, so that information also is we can see from this solution. Okay. Now this is another example, is that this case is initially is that let's say you have a diode. This is a PN diode. Okay. Initially, the diode switch was applied to the A position, which means that this is the forward bias, so that the current is IF. Okay, so initially diode was the forward bias. Okay, and then at the t equals 0, okay, we're gonna suddenly change this switch to the B position. Okay. So when we change to the B position, now what we can see from this circuit, the diode is that the reverse bias in here. Okay. So when this one happens, now we are also interested how the stored charge going to be changing, and also how the current flow affected by this switching characteristic. Okay. That's we want to see in here. Okay. To look at that one is that this is the simplified configuration for this P plus N diode. Okay. Now, is this one case in terms of current, if I show you, is that this is a T. Okay. So initially is that the current was that it flow with IF. Okay. And then T equals 0, we're going to suddenly change this one to the minus IL. Or in here is IL. Okay. You change the IL, it's like this. Okay. So when you have this sudden change of this current, we are interested how this charge is going to be changed. Okay. So to look at this characteristic is, again, we're going to start with the same, is same equation in here. Okay. So our equation in here is that from the Hall concentration change is that when the T is larger than the T equals 0, okay, then our current is changed to the negative this IR. Okay. And then you have the QP and then QP over tau P and following this equation. Okay. So this equation, same way, represent the continuity equation for the whole. Okay. Now, as a boundary condition in here is when the t equals 0, okay, or before t equals 0, the diode was applied as the constant IF. Okay, so it was applied with a constant IF. So from there, we can have the charge in the diode approximate with a tau P IF. Okay, same way as we did in before. Okay, so this one serves as the first boundary condition for our case in here. Okay. Now, another boundary condition is that when the t goes to infinite, okay, when the t goes to infinite, now is, as you can see, is that you're going to reach to the steady state, okay, and then the QP, this one is, you can have is t goes to infinite, you will have negative IR and then the tau P, okay. So you have same way, you have two boundary condition, and then you're going to apply the same, is that solution for the QPT, like we did before, A plus B exponential minus T over tau P. Okay? So using this general solution for the QPT, we can obtain the coefficient for the A and B. Okay. So if we do that one, now is the result for the solution going to be this equation. QPT going to be this equation. Okay. Let's check whether this equation satisfied our boundary condition. So when the t equals 0, okay, so if we put the t equals 0, okay, then now is this term is 1. Okay, so then in here is the tau P IL, negative tau P IL, so these two is go, so you have tau P IF. Okay, so that is the first boundary condition we saw in here. Okay, so that is correct in here. Now, second one is that when the t goes to the infinite, okay, so when t goes to infinite and the whole this term goes to 0, so now our solution going to be negative tau P IR. Again, that satisfied our boundary condition. So we can conclude that this solution is correct. Okay. So this way is that now is our whole concentration will be changed as a function of time. In here is that if we look at the graph, how is the charge going to be changing, is that we can have this kind of graph in here. This one is in terms of whole concentration. So initially is that we have the current is that flow with IM. So this is right before the time equals 0, right? So at that time, for these constant forward bias, if you look at the whole concentration change in the N side of the PN diode, then you will see that your whole concentration going to be exponentially decaying following this curve. Okay, and then keep in mind that this slope in here at this is a depletion edge, x equals xn. Okay, at this depletion edge, the current, this one, whole current, that related with this slope, okay? So the slope, positive, the slope represent this IF in here. Now, at the t goes to is at the t equals 0. Now at that point is we change the switch to the reverse bias. Okay, so that the current in here is changed to the negative IR. Okay. At that moment is that to represent this negative IR, your hole concentration, especially is the depletion edge, that this slope is changed such a way to get this negative IR. Okay. Now, during this time is that, as you can see, is that your carrier concentration, hole concentration is getting smaller and smaller from forward bias. Okay. One thing we notice in here is the hole concentration. This one cannot be 0 suddenly. Okay. It takes time, this hole concentration go to 0. Okay. So as this graph shows in here, as the time passed, initially it was forward bias following this red curve, and then now is when the switch is in the reverse bias, concentration is decreased as the time passed like this. Okay. And then at some point is, as you can see, is that this change is going into the reverse bias, okay, which is that below than your thermal equilibrium value. So when you look at this hole concentration, excess hole concentration, when this one reaches to 0, okay, or is that we can say that total stored charge in this n side, when this one is 0, okay, at that moment is that, as you can see, that all the stored charge due to the forward bias in the p-n junction diode is actually gone in this n side. Okay, and then after passing that time is we can say that the diode is that reached to this reverse bias condition. Okay, so this one implies that even though from the out, if you look at our so switching structure in here, is that before time equals 0, diode flow the current as this is IF, forward bias current was flow through this p-n diode. Okay, so when the forward bias current flow in here, especially in the n side, we're going to start to see that the hole, number of holes, this one is increased. The minority carrier in the n side is increased due to this forward bias. Okay, and then that way is that it stay there. Now, at the t equals 0, we're going to suddenly change this switch to the reverse bias. Okay. Now, from the outside, we suddenly change this one to the reverse bias. So our current is changed to this negative IR. Okay. During that time, is that this n side hole concentration cannot suddenly change to the reverse bias, the thermal equilibrium value. Okay. Instead, the hole concentration in here is change slowly and then eventually going to the reverse bias condition. Okay. And then that change followed by this kind of a graph. Okay. So during this time is if you look at the diode is until the total number of charge in this N side, total number of this minority carrier charge in the N side is at the positive. Diode itself is filled as the forward bias. Okay? Because at the forward bias is that your minority carrier concentration is larger than the thermal equilibrium value. Okay? So during that time is that when you look at across the diode is that still remain as the forward bias, this condition. Okay? Now, at the T equals in here is the TS represented in here. At the TS, your total this excess minority carrier concentration is going to be 0. TS, QP going to be 0. Okay. That moment is now diode turned into the reverse bias. So when you look at the voltage across diode, now diode is that the voltage is going to be changed. And then eventually it leads to their reverse bias condition. Okay. So that kind of characteristic is we can obtain from this switching characteristic. Okay. And then if you look at the current flow across the diode is before t equals 0, again, its current was IF. Okay. Now, at the t equals 0, we suddenly changed the diode to the reverse bias. Okay. At that moment is that the diode is still remains as a forward bias, so your current is limited by the outside circuit. So in other words, if you look at the configuration in here, t equals 0, we suddenly change the switch to in here. Okay. At that moment, diode itself is still remain as the forward bias, which means that in the forward bias, the resistance, the diode, is very, very small. Okay. So the current is mostly limited by this current, limited by the negative VR over R outside the circuit. Okay. Now, as the time goes, that when the diode is turned into the reverse bias condition, which means that all the excess, those minority carrier is all gone, then, as you know, is that across the diode, the resistance going to be increased. Okay. Now, when this resistance is increased, your total current, T, is limited by this R across this diode. Okay. And then when this one is increased, now your current is decreased. Okay. So, due to that effect, we will see that this kind of curve is that the forward bias current condition, when the switch is changed to the reverse bias, then suddenly you flow the negative IR, and then it remains with the negative IR as long as the diode still feel itself as the forward bias until all the charge is gone. Okay, so that's the time in here, TS. Then after passing this time, is that you're going to start to see that the resistance across diode is increased, so that your current is limited by this reverse bias current. Okay. So your diode, the characteristic of the current following this abrupt change like this. And then TS especially, we can calculate from the previous obtained the charge. So this is actually TS. So total whole discharge equals 0. At that moment, we define the T equals TS. Okay. So if we plug in that one in here, this is 0. Then from there, we can obtain this T. Okay. And then that followed at this equation in here. Often, this in our case is that TS. We want to have this one is as small as possible to obtain the ideal switching characteristic. Okay. So if you look at this equation in here, is that to make the TS as small as possible, either you can use the material which has the tau p is a very small value. Okay. So typically this one happens that in the diode, if we put some defect there, we can actually reduce this carrier lifetime. Okay. So by that way is that we can reduce the tau p to improve this TS response. Or we can have the different is this outside circuit parameter to reduce the IF or increase the IR. So that way is we can adjust the switching characteristic of this PN diode characteristic. Okay. So that kind of information is that we can obtain from this cup. Okay. Okay, so this is the end of this switching characteristic. So basically, our first exam will cover up to this slide. Okay. So do you have any questions so far? No, no question. So we have 7 minutes left. Let me see. Okay. This one is the same as I explained. Switching characteristic is this way. Okay. And this one is this graph is showing that how the minority carrier concentration will be changing. Okay. So especially this the first the A graph, this one is showing that the P plus N diode case. Okay. So how do we know is when you look at the minority carrier concentration, as you can see, is that the electron concentration in the P side is much smaller than the hole concentration in the N side. So we can conclude that this is going to be P plus N. Okay. Now, when you apply the forward bias, as we discussed, the concentration will change with the equation we discussed. So, for example, is how much this?
Professor,
Yes.
is
Okay,
there anything the all forward bias is P plus N type semiconductor?
No, it's sometimes we just use the PN diode, or it depends. Is that
Okay.
Is the device structure.
Okay.
But the reason is why I look at in here is the P plus N is that we can by using this configuration we can approximate the total current going to be this way. So our derivation going to be much simpler.
Okay, thank you.
Okay, okay, then that's good. So when you forward bias, as you know, as we discussed, we have exponentially decaying like this, okay? And then as a switching, if we suddenly to the reverse bias, at the end, in the reverse bias, your carrier concentration follow the smaller than your summary equilibrium value, okay? But from the forward bias to the reverse bias, you need to have certain transition time required, okay? And then as a switching device, typically we try to minimize this switching time in the structure. Okay, so then that's good. Any other question? Everything is okay? Okay. Then maybe I think, as I mentioned, is that I'm going to send you another homework this Wednesday. Okay. And then based on our plan, next following Wednesday is that I'm going to review the homework and then our class. So if you have any question, you can ask a question during the time. And then 2 weeks later, Monday, we're going to have our first exam. Okay? So I think that's it
Professor,
for
as you
today.
said,
Yes.
you're gonna send,
Oh, pardon? Can you say that
Professor, you
again?
said like you're gonna send the second homework. So
Yes.
the second
I'm going to
homework.
send you the second
So I
homework
don't.
this Wednesday.
So I don't receive your.
Oh, no, not yet.
So I will
Not
send
yet.
you because I don't receive your email. So I'm gonna.
Okay, yes. Okay, yeah.
I'm
Anyone
gonna
who
send
do
you.
not receive my email, please send the email to me, okay? So that I can put your email correctly so that when you have exam, okay, you can get the exam by email from me, okay? Okay, so if you do not have any other question, then I think we're gonna end today's class in here, okay? And then see you next Wednesday then.
Thank you, Professor.
Okay, thank you guys.